vector math. Adding and subtracting vectors. Suppose we have the vectors u, and you can add an arrowhead over top of each of these. Suppose you had the vector u and the vector v. One of them is 5, 0, and one of them is 4, 5. U plus v can be interpreted this way. You're first going in this direction. I'm going to just take that arrow and just move it somewhere here. This is what I'm doing first. And then I'm doing this one. So I take this, put an arrowhead on that. I'm doing this second. Can you see that you would have started at this red point here, and you would have ended at this purple point there, hence making this, oh, I like colors today, orange vector as a result. That's what happened in the end. You started at the red dot, you ended at the purple dot. So when we're adding vectors together, it means first you went in the u direction, then you went in the v direction, and you ended up just like you had gone in the orange direction to begin with. Now, if I look at this orange vector as a result, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right and 5 up. Okay. 9 to the right and 5 up. And you guys are somehow going to miraculously tell me how I could possibly have figured this out if I had taken u and added v. There's obviously some complicated math going on here. Somehow adding those together gave me 9, 5. Right? But that's maybe it's beyond the scope of this course. Or maybe we just added the x's together and added the y's together. Can you see it? Does it seem overly simple? That's because, yes, it is overly simple for adding vectors. So the resultant vector u plus v is the third side, and we always, when we're adding vectors together, it's important that we attach the head of one vector, so here's the head of the red vector, to the tail of your next vector, and then the resultant would be u plus v. So u and v are placed next to each other, head to tail, head of the first vector to the tail of the next vector. Kind of sort of feels like common sense that way, which it's good, it is. Order doesn't matter. U plus v is the same as going v plus u. So if I go back to this one here, which I drew it out in green, and I said I decided to go green first, and then go red second. It ends in the same spot. It doesn't matter the order you do vectors. Matrices, adding and subtracting didn't matter the order, but multiplying was like problematic. But vectors, doesn't matter which direction you go first and which one second. Excellent. So the resultant vector is 9, 5, and here, I gave it away. I knew some of you were reading ahead and saw that terribly complicated pattern that you just add the components together. And I'm sorry to say, but subtraction of vectors is just as easy. So if you were looking for something complicated, but we're still, right, the subtraction of vectors now is that u minus v is like taking u, which is still 5 to the right, but minus v is v in the opposite direction. Now it'd be -4, -5. And again, you probably can see from the math that it is not hard to see where those answers come from. And if I went 1 to the right and 5 down, that matches up perfectly with that blue vector. So just subtracting the components works the same. But we still draw it like we're adding a negative vector. Does that make sense? Like vector u is the green one. Then we add, so we put head to tail together because that's what adding does. But we add the negative v vector, which is just the same v vector but in the opposite direction. Yeah, I guess I just said that. So if A is 2i minus j, B is I plus 3j, find and draw the following. All right, well, this is not too hard to do. So if you wanted A plus B, you draw A first, then there's A, the blue one, then add B, the green one, and you get A plus B, the red one. Again, if I was doing the math for these, I would probably change them to column vectors. Here's A, 2, -1, plus here's B, -1, 3. Is it easy to see that the answer is going to be 1, 2? Did this go 1 to the right and 2 up? It does. They're all free wherever they are. So unless you're dealing specifically with coordinate, like with position vectors that say I've got things fixed in place, one of the powerful things about vectors is it says you can solve it anywhere and it should apply to the situation over here as well. I feel like you don't need to write them all down. You could do the other ones on your own if you wanted, right? So let's get to something more fun, which is 3 dimensions. And if you wanted to do P plus Q, that would be really easy. P minus half of Q, you could cut this one in half and then add. Any kind of numbers in front just would double and triple them. So if we know what A to B is in 3 dimensions, and B to C, let's find A to C. So I find that drawing a picture of these things, maybe I'll even color code it here. I'm going to make A to B in green, and B to C in red. Then A to C is what's left in blue. Well, if I can get from A to B, and then I can go from B to C, that's the same as going from A to C. So A to C, I probably have it written here. A to C has to equal A to B plus B to C. Vectors aren't, again, worried about where you went in between, just worried about where you ended up. They're not like your parents. Your parents are like, why did you go there first? They're more concerned about where you're in between sometimes, right? They're like, well, as long as you got to school, I don't care that you took a flight to Paris in the morning, and then came back, you got to school on time. As long as you got to school on time, right? Now, vectors aren't even worried about time. They're like, who cares about the time? You started at A, you ended at C, life is good. So then we can take our vectors and just add them together. And again, the column vectors make it super easy, because it's like adding matrices, right? Vectors are like very simplistic little matrices that you can add together. Yes.
So, sorry, this concept is different from the one we did previously, because previously we were using position vectors.
Position vectors are fixed, yeah.
They had a fixed point, but because these are free,
Yeah.
we can just simply add them together.
We can just simply add them together where they are. Technically, if we wanted to put them in chains and make these vectors not free, we could pick an origin somewhere. And then you'd have a position vector A, a position vector B, and a position vector C. And let's say you have a robot that can only move in those directions. It can't move in any other directions than the black arrows. This is what we're going to get to next. Right? It's a kind of dumb robot. It doesn't have much movement availability, and you want to go from B to C. Well, you would tell the robot, go back to O, then go to O, go to C. If you wanted to go from A to C, you would say, well, start from A, go back to O, then go to C. If you wanted to get to, and this is where we're going to have fun, if you wanted to get to the midpoint between B and C, but you could only travel in these directions, well, go halfway back to O and then go halfway to C, and you'd get there. So we're going to figure out how we can get to any point we want, but being restricted to certain position vectors or certain directions to start with. But yeah, as soon as if we would add an origin and fix them in place, then we have a little bit less freedom and would only be allowed to travel along the black arrows. But if we take that away and they're free, like, oh, if I can go from A to B and I can go from B to C, then I can go from A to C. Okay. So we've got AB and AC. Find B to C. So we can draw this out. We've got AB and we've got A to C. Those are the two red ones. We want to go from B to C. Well, if I want to go from B to C, and I have to use the red ones to get there, can you see that I could go from B to A by just making that one negative? And then I could go from A to C. So B to C will be B to A plus A to C. And then B to A is negative A to B, and now I can plug in numbers for those and get my results. The zero vector. You know how there was a zero matrix? Matrix with just a whole bunch of zeros? Well, we have a zero vector as well, which very much like the zero matrix, just has a whole bunch of zeros. We show the zero vector with a zero with a vector over top of it. Right? If you went from P to Q, and then went from Q to R, and then went from R back to P, I guess technically you would get the vector PP. Because you started at P and ended at P. But that's like you haven't gone anywhere. This is the zero vector. Right? So in vectors, it's sort of like where you started and where you end is what's important. I think this is why I don't like going for runs. Because if I'm gonna, I know it's good exercise and it'll probably make me a better soccer. Like it has a lot of good things. But in my head, in vector perspective, I start at my front door, and then 10 minutes later, I will be back to my front door. I could do that a lot quicker if I just didn't go anywhere. And so, I think that's why I don't like running. I like running if I have to get somewhere, and it's and I don't have a car, and it's in a hurry. Then the running seems like a logical thing to do. But just going for a run, I could have got back to my house a lot quicker if I would have never left. And that's what vectors are saying here. You did all this work and you got nothing because you are right back to where you started. So these are, called our zero.